Okay. So, interpolation means I have got this low rate sequence, this sample, this sample, this sample, this sample like that, and these red color samples are to be recovered, okay, from this low rate sequence exactly without any error. Okay, I am told one thing that originally sampling frequency, that sampling period was tau, sampling frequency was 1 by tau, but that was above the Nyquist rate. So, there was no aliasing originally, therefore, if I increase the sampling rate further, no question of any aliasing. So, now one thing that suppose originally you have got this sequence x n, okay, and what is your, it is given that analog Fourier transform. Again, I am drawing analog, I should draw magnitude and phase separately versus omega, because it is a complex number, complex quantity cannot be described by one plot. But nevertheless, just for explaining my point, as I always say, I am showing in one plot only. Suppose it is given like this, it is a band limited function, maybe something like this. This is your band limiting frequency. So, your sampling frequency, in order to avoid aliasing, should be at least twice omega each or more. So, I start with the extreme case, I mean borderline case, that is omega s. Omega s is 2 pi into sampling frequency f s, and f s is 1 by tau. Okay. So, this is that. The omega s, I am taking the case where omega s is just twice this. So, verge of aliasing, say. Okay. Omega s could be to the right, and omega s could, I mean, if omega s is here, it is twice omega h. So, omega s by 2, that is half sampling frequency will be here, coinciding with omega h. If omega s is further to the right, omega s by 2 will be somewhere here. So, there will be 0. So, in that case, we can assume that original analog Fourier transform is up to this, it takes a shape like this up to this. So, this is like the band limiting frequency now instead of this, and omega s by 2 coincides with this. Okay. But in our case, I am just taking the example where omega s is here and this is equal to omega s by 2, this point, alright, omega s by 2. No question of aliasing, because omega s is twice omega h, the band limiting frequency, this original Fourier transform is 0 here, has magnitude 0. So, sampling period, sampling frequency I am taking to be twice that band limiting frequency. So, Nyquist rate, no problem, no aliasing, alright. So, in that case, if I sample, what will be the DTFT? We have seen DTFT will be no aliasing, it will be replica like this. This half sampling frequency always go to pi and minus pi, but since half sampling frequency is same as band limiting frequency, so band limiting frequency will also go to pi and minus pi like that, and then there will be periodic repetition. Dot 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 dot, right. That is the DTFT of this guy, that is original x e to the power j omega, where x n is this low sampling rate sequence. But suppose I had sampled the original analog waveform at a faster sampling rate. So, smaller sampling period is now tau by m, earlier this much was tau, now tau by m, or equivalently sampling speed, sampling frequency, sampling rate has gone up by m is an integer. That is why between two samples, original samples, I now have m minus 1 sample. So, if this was tau, now it is tau by m. So, this becomes mth sample, alright. Then for this sequence, that is this sequence, what is the DTFT? That also you have to see, there will be no aliasing. So, the DTFT again will be replica of analog Fourier transform, but it will have a different shape now. What kind of shape? Now, nu omega s, you can call it omega s, nu omega s, that is m times original omega s. Nu omega s by 2, if you call it omega s prime 2, that is m times original omega s by 2. Now, but I know half sampling frequency, whatever is the sampling frequency employed, half sampling frequency will always map to pi, right. So, this will go to pi. and this will go to minus pi. Okay. But this is now m times omega s by 2, and original omega s by 2 was same as omega h. So, m times, this is equivalent to m times omega h. Okay. So, if this maps to pi, omega h will map to pi by m. So, maybe I draw according to scale, put the pi here because it was pi here, and put the minus pi here. Okay. So, this is a new pi means it is the mapping of omega s prime by 2, new half sampling frequency, that is mapping to pi. Okay. But earlier this pi was the map of omega s by 2, that is original half sampling frequency, also the map of omega h, because they were same and there was no aliasing, you see. But now new half sampling frequency is omega s prime by 2, that will in any case map to pi, but that is m times original half sampling frequency, which means m times original band limiting frequency. So, if half sampling frequency in the analog domain is m times original band limiting frequency, so map of half sampling frequency, which is pi again, that will be m times the map of omega h. That means omega h will now map to pi by m, and then zeros, because outside they have 0. Okay, these zeros will come. Okay, these zeros, because omega is now going to right side m times, omega s prime to somewhere here, that will map to pi. Okay, omega s was here. Now, if you go to the right, somewhere here is your omega s prime. So, earlier omega s by 2 was here, now omega s prime by 2 will be somewhere here in, okay, that will map to pi, and this is m times less. So, that will map to pi by m, and the intermediate zeros will come here. All right. This is the situation. This is the new DTFT. Okay. So, again at 2 pi, around that you have got things like that, 2 pi plus pi by m, 2 pi minus pi by m, here also dot 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 dot. That is the DTFT of this higher sampling rate sequence, interpolated sequence, higher sampling rate sequence. Now, my claim is, if by the processing this low sampling rate sequence some way or other, I give you one sequence whose DTFT is this, then that must be the desired interpolated sequence, high rate sequence, because DTFT corresponds to only one time domain sequence, not many. So, if I can generate some sequence whose DTFT is this, then that must be equal to this, that sequence will be equal to this only, because one DTFT means by inverse DTFT you can get only one sequence, not more than one. All right. So, now I will process this original low rate sequence and generate finally one sequence whose DTFT will be of this kind, which means that final sequence will be nothing but this. That will be the interpolated sequence, and between every two blue colored sample you will get these red colored samples. Okay. How to do that? I am coming. So, here I will be using this expansion. So, my first step here is expansion. This is your xn, I expand by m. That means, what was expansion? Expansion was, you see, if you have a sample x0, x1 and intermediate sampling points, I do not have those samples. I am looking for those samples now for interpolation, I do not have. So, I was putting zeros there, m minus 1 zeros. So, sample number 1 is now sample number m, then again m minus 1 zeros. So, sample number 2 is now sample number 2m, dot 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 dot. So, for this sequence, this is called expansion, xen and xn. Okay, xe m, xe1 is 0, 2 is 0, 3 is 0, up to m minus 1 0, xem is x1, xe2m is x2, dot dot dot. Then I worked out this summation capital Xez, there is z transform of this expanded sequence which has zeros between every two samples m minus 1 zeros, that is original z transform x at z to the power m. So, complex value is not z, z to the power m, whatever is the value that will be the z transform at z for xez, and therefore, z equal to the power j omega I took for DTFT, and that was capital X to the power j omega m. So, omega into m, radian into m, that is another radian. So, omega into m at that digital frequency, whatever is the value of this DTFT, that will be the DTFT of this expanded sequence at that omega. That is what we did. And now I am expanding. Okay. So, by this formula, here if I have x e n and if this is x e to the power j omega, this will be x this e to the power j omega m. Okay, because DTFT of this is x to the power j omega. That is what we derived here. Okay, that is the only thing I borrow from there. Now, I have shown, I have taken this to be my original x a j omega, right? And this was my original x a j omega. This was sampled at just Nyquist rate, and that was the DTFT. Okay, that was the DTFT, x e j omega. So, what is x e j omega m? If this is my x e j omega, what is x e j omega m? So, I plot it. Okay. Now, as before, x e j omega e to the power j omega is a function of omega, right? You call it f of omega. Then x e to the power j omega m, it is nothing but f of not omega but omega into m, because wherever omega was coming, that is to be replaced by omega m, and you call it some function g omega. I have to plot g omega versus omega. I have to plot this g omega versus omega, right? G omega is this guy, which is f omega m, which is g omega. I am just giving a name g omega. How to plot g omega? Now, here you see at g omega at say omega equal to some omega by m, omega by m. What will be the value? If you put omega by m here, m cancels, f omega. And what is f omega? Original x e j omega. So, original x e to the power j omega at any omega whatever value you have, that will come to g omega at omega by m. That is, any g omega at any omega by m is same as f omega. That is capital X to the power j omega. So, capital X to the power j omega at any omega whatever the value, that will come to this g omega at omega by m, that is for this function at omega by m, which means pi will come to pi by m. Minus pi will come to minus pi m, 2 pi will come to 2 pi by m. This will be like this, dot 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 dot, final will be from pi to minus pi. So, either it will go like this, or it will go like, it will be either, if it is pi, it will either end like this, or it will, if it is pi, it will just go like this on this side, depending on whether capital M is odd or even and all those things. Okay, but you will have this kind of stuff. But that means, if I expand, the DTFT will be this. But for interpolated function, for this interpolated function where I do not have zeros here, I have exact samples, the interpolated function. What will be the DTFT of that? That we have already worked out. This is the DTFT. Then I told you, by processing xn, I already processed xn, generated the xen. By further processing, if I can generate another sequence whose DTFT is this, then I am done, because DTFT this means in time domain this will be the sequence, because one DTFT corresponds to only one sequence. Now, I have gone up to this. If you compare these two, that you see this minus pi by m to pi by m, this part is common, but other part is 0 from minus pi to pi, which means if I now pass this sequence to an ideal low pass filter, ideal LPF, low pass filter of this kind, pi by m minus pi by m, and then 0 up to pi, 0 up to minus pi. This is the DTFT. h to the power j omega, right? It looks like this, pi by m minus pi by m 1. So, whatever comes in this band it passes, and then 0 up to pi, 0 up to minus pi. If I pass this xen through this filter, okay, then what will happen? This sequence has this DTFT, but if it passes through that low pass filter from minus pi by m to pi by m, so only this much, this is the bandwidth pass band of that low pass filter, and then it is zeros. So, you will get only this much present, other parts will be 0, and this is what we wanted. Minus pi by m to pi 0, pi m to pi 0, minus pi by m to minus pi 0, and then again repetition of this. So, this is the way you can generate this interpolated sequence, all right, provided of course you have got ideal filter. If it is not ideal filter, then some part from right and left will filter in, and they will create some error, aliasing error and all that. Okay. So, these two are very important topics, decimation, interpolation. Now, I go to another important concept in multi-rate signal processing, that is called polyphase decomposition. Suppose I have a sequence. I have x 0, then x 1, dot 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 dot, x m minus 1. So, 0th, first, second up to m minus 1. Then again I have at mth point x m, then m plus 1, so 0 to m minus 1, m to 2m minus 1, okay, you have to just add m plus 0, m plus 1, m plus 2 up to m plus m minus 1. So, this is your, let me draw by black ink. Then again at 2m, x 2m, dot 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 dot. Nothing new, I am just drawing the samples as it is. On this side also you can draw. Okay. Now, suppose I pick up the 0th guy, okay, then mth guy, 2mth guy, minus mth, all that. That is, I decimate it by a factor m. So, 0th sample, then throw away the next m minus 1 samples, take the next guy mth, then again forget the intermediate samples, m minus 1 samples, take the 2mth, like that. If I do like that, I get a sequence which I call polyphase component, 0th polyphase component, 0th polyphase component of xn. It will be like this. I can just write in terms of samples x 0, that will be the, we sometimes do like this, instead of showing it by a diagram like this, we point like this. This is the origin x 0, sample number 1 is the next, that will be your, if it is origin, forget about this next m minus 1 samples, I take this one, say, okay, then x 2m, from here it is x minus 1 dot 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 dot, and this is the origin. This is called the P0n. P0n means 0th polyphase component of xn. Okay. Then suppose I have okay, reading this fine. I take next one P1n. I take this sample x1 x m plus 1, that is at a gap of m, x2m plus 1. So, this cross you see x1 m plus 1 2m plus 1 at minus m plus 1, these guys, and form a sequence again x1, but that even though this is sample number 1, here this is my origin 0th sample. Okay. So, I am constructing a subsequence P1n where x1 will be the 0th sample. So, then x m plus 1 will be the sample number 1, like it was sample number 1. You understand the sampling rate has gone down here. After 0, I am jumping. So much of time, then only x m, then so much of time. So, like that 1, then m plus 1, 2m plus 1, dot 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 dot. All right. In general, PLN will be what? You might take one Lth sample L x L from 0 to m minus 1, then from m to 2m minus 1 again there will be this L. L means L plus m now, jumping from here. So, x L plus m, then somewhere here is x L plus m, L plus 2m or 2m plus L, whichever way, all right, 2m plus L at this point. Here also x minus m plus L. That is a general case. L could have been 0, I am here P0n. L could have been 1, so I take x1, then here x m plus 1, like that. L is general L, xl, so xl, m plus L or L plus m, 2m plus L, minus m plus L, like that. So, general case. So, again I construct a sequence using them, but xl will not be the Lth sample here. Again I will put it at the origin in my new construction. And lastly, you see you start with 0, m, 2m, like that, 1, m plus 1, 2m plus 1, like that. Finally, you will end with m minus 1, then m minus 1 plus m, that is 2m minus 1, 3m minus 1, like that. You do not go to m again, because that is already taken care of in this, xm is already present here, all right, xm, x0, so there is already P0n. So, you will be stopping here at this x is origin, this instead of L it is m minus 1. So, it is 2m minus 1, it is 3m minus 1, just L is replaced by m minus 1 here. L was 0, L was 1, L is m minus 1. So, everywhere minus m plus m minus 1, so x minus 1 dot 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 dot, not dot dot, this dot 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 dot. Okay. So, this is called 0th, this is called first polyphase component, Lth polyphase component, this. Now, using them, how to get back this? you will see if I expand this P0 n, then between every pair of samples I bring in m minus 1 zeros. Okay, that is I expand P0 n, what will I get? X 0, then zeros, m minus 1 zeros, then x 1, sorry, x m, this guy, again m minus 1 zeros, again 0 0 dot 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 zeros, x, sorry, this is not, this is wrongly written, this is x minus m. Dot 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 dot. All right. Then again, suppose P1 n, this also I expand. What will I get? X1 as it is, then zeros, then x m minus 1, x 2m minus 1, x minus m plus 1 dot 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 dot. Okay. Suppose I delay this I delay, this output, this was here, right? If I delay it, what will happen? This will go to the next, this will go to the next. So, you will have this 0 will come here, so you will have 0, x 1, then the zeros will move. Below this, there will be 0, x m minus 1, this will come here. Then again 0 0 0, 0 will move here, x 2m minus 1 will go there, like that. This will come here, then zeros, 0 from here. Okay. If I delay by 1. Now, if you add this and this, if you add, what will you have? X 0 plus 0, so x 0, x 1 plus 0, x 1. Then of course, zeros with zeros, zeros. Then x m, now below there is a 0 has come, this has moved to right. So, x m plus 0, x m minus 1 plus 0, x m minus 1. So, this way if you see, you will have, if you add the two, then you will get x 0 coming here, x 1 going here, then some zeros, then x m minus 1 has come here, then some zeros. Obviously, it will be one less 0, earlier it was m minus 1, now it is m minus 2, okay, because you are adding x m with 1 0 or x m minus 1 with another 0, so zeros are getting absorbed there. Okay. This m plus 1, again I am making a mistake, m plus 1. See again, in case you have doubt, x 1, this guy at 1, then 1 plus m, you jump to the right by m, so x m plus 1, jump to the right by m again, 2 m plus 1. That is why x 1, m plus 1, 2 m plus 1, jump to the left by m, so minus m plus 1, like that. Okay. So, it is actually m plus 1, 2 m plus 1, then again zeros, x minus m, x minus m plus 1, zeros, dot 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 dot. So, you see, if you compare x 0 it has come up. X1 has come up, but then we have zeros. Then again Xm has come up. Xm plus 1 has come up, but then again all zeros. Then again X2m, 2m plus 1 have come up. Then again zeros, like that. Okay. So then if you see, if you expand next one, P2n, you will have x2, just expansion will be x2, xm plus 2, x2m plus 2, like that. Okay. And if you delay it by 2 times now, if you delay it by 2 times, then x2 will go here. Okay. Xm, then jump to the right by m, xm plus 2 will go here, x minus m plus 2 will go here, and there will be zeros. There will be zeros below them also, like that. The zeros, if you add this plus 0 this plus 0 this plus 0 this plus 0 this, like that. So you will have that will be further constructed, I mean, you will have x 0 followed by x1 followed by x2, then some zeros, then again xm, m plus 1, m plus 2. Dot 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 dot, there are zeros and all that. This side also 0 0 0, then you have got x minus m plus 1, x minus m plus 2, dot 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 dot. Okay. So again x0 will be there, x1 will be there, x3, this 3 will be there, 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 like that, So as you go on doing it, finally when you add, these zeros will go and then entire sequence will be built up. So you will see that you can get by, if you try yourself, you will see you will get xn by this method, that is p0n then p1n, as I have done, but I will shift it by only 1. P2n, I will shift it after expansion, I will now shift it by 2. In general, PLN that is where minus L dot 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 P n minus 1 n sorry, m minus 1, yeah, m minus 1 n, and if I add this with this and this with them, so this way if you go on adding, this of course is nothing, this adder is not required anyway, because this is a 0. This will be your xn. All right. If P0 n has got Z transform capital P0 Z, what is P0 n? We have already seen 0th guy, mth guy, 2mth guy, like that. P1 n, first guy at the 0th position, m plus 1th guy at the first position, 2m plus 1th guy second position, like that. P2n means second guy at 0th position, m plus 2th guy first position, like that. So if this, say PLN for that matter, has got PLZ in general, PL by the sequence as PLZ. After expansion, expansion means what? I am plugging in zeros, m minus 1 zeros between every pair of sample. We have seen expansion. If you do this, if the original Z transform is say PLZ, it becomes PLZ to the power m. We have seen expansion today. That is, between every pair of sample, if I bringing m minus 1 additional zeros, it's a high speed sequence, only intermediate sample values are zeros. So, the resulting sequence will have a Z transform P L Z, resulting sequence will have a Z transform which will be original P L, but instead of Z, Z to the power m. Okay. So, this will be P 0 Z to the power m. Okay. This will be P 0 Z to the power m followed by delay. So, Z inverse P 1, sorry, not P 0, P 1 Z to the power m. Here it will be capital P 2 Z to the power m after expansion, then Z inverse 2. So, it will be Z inverse 2 P 2. Here it is again capital P L Z to the power m, then Z to the power minus L. So, Z to the power minus L, and lastly here again P m minus 1, capital P m minus 1 Z to the power m, and then this delay. So, it will be so if you add all of them, you get Z transform of x z, which also shows x z is P 0 polyphase component, 0th polyphase component, but expanded. So, there is Z transform. Then one shifted version of, you take the second polyphase component, but expand it, and then one shift dot 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 Z to the power L minus L P L Z to the power m, that is you take the Lth polyphase component, expand it, but you have to shift it for proper placement, shift it by L to the right, that is why this, and lastly, sorry, this is called in the Z domain polyphase decomposition by a factor m. Each of this is called, in fact not Z to the power m, each P L Z is called the Lth polyphase factor of x z. Okay. Not P L Z to the power m, you make it Z to the power m in the summation. Just P L Z is called the Lth polyphase factor, and this is how this decomposition is called mth order or factor of m polyphase decomposition of a given Z transform x z. We conclude here today. We will then combine this decimation, interposition, expansion and this polyphase decomposition to build some efficient structures in the next class. Thank you very much.